Okay, thank you very much, Andre. It's a real pleasure to be here. I just want to say how much I've been enjoying this workshop. I just feel like there's a lot of really exciting developments and thinking going on. It's very motivating to me, and I hope everybody feels the same way. So my talk today is just going to be a bit broad, and I'm also going to be talking about, or at least half about other people's work, but I hope that's useful to everyone. So the basic message, and this doesn't need to be said to this audience, is that tensor networks are turning out to be a very natural way to parameterize machine learning models. And I would say a very interesting one. And my point of view is that really the best is yet to come in this field. And I'll say this a lot more at the end, but I think something particularly exciting is that they offer the chance to really understand things like what has a model learned, what is a good way to think about learning, understand regularization landscapes, but really to develop better and better algorithms that not only say are faster, but are more insightful. So I think that's something that is particularly exciting to me. And this talk is to give a perspective on this topic from more of my area, which is coming from physics and then coming out of physics and viewing these tools more broadly as function approximators. But then what can people from a physics background offer to the rest of you in terms of some ideas or perspectives. So then the breakdown of the talk will just be a little bit of background and notation, and then I'll spend a while going through some recent applications that go beyond Tensor Train's matrix product states, showing how there are some nice architectures that are already becoming very useful and powerful there, and then some ideas about algorithms and some developments there and some perspective. So first of all, just by way of review, tensors emerged all over the place in machine learning. And so just a few examples would be, one example we saw yesterday talking about tensor completion was taking the perspective more of thinking of organizing data into tensors, which is very natural. So you could have, for example, more heterogeneous data. It's much more natural if you have, say, 4 different factors in medical data to have an order 4 tensor, rather than trying to shoehorn this into a matrix or something. And you might be able to find more relationships between these factors or features if you view it as a tensor and use better algorithms. Another setting, this isn't what I'm going to talk about, but just to show how broad it is there's work about within the use of neural networks to enhance them or to understand them or improve them by tensorizing some of the layers or some of the parameters, so the weight layers, say, by doing these mappings where you map a large number that's like a power of 2 to the product of n 2-dimensional things, like this kind of idea. I believe it's called quantitization or quantics, more in the math literature, if I'm right about that. And then to decompose this large tensor of the weight layer using like an MPO tensor network or these kind of concepts, and get scaling or efficiency advantages that way. And then last but not least, the more of the concept I'll be focusing on is to use models for machine learning where the weights interlinearly. So you can think of these as variants of kernel learning, but with a pretty different goal, a pretty different approach, where you're not so much going to then do the kernel trick and think about gram matrices and these kind of things, but you're going to just directly parameterize the weights as a large tensor because your choice of feature map leads to that being the natural form of the weights. Then you're going to try to compress the weights a priori with some kind of tensor network, and then see where that leads you, like whether it's just that you get more efficiency, but also maybe you can get better algorithms and get better insights and things. Which leads me to ask, what's appealing about tensor networks? So first of all, a tensor network is the idea of that you have some target tensor, which maybe you actually have, or maybe you are thinking about as an idealization of some object. And then you want to represent it, here there could be more of an approximately equals, as a contracted product of a lot of smaller tensors that have a lower order, hopefully, so that you can work with these and store them, and it's efficient to do this. You might either start with this tensor and obtain this network, or you might just start with this network at the outset and try to optimize the numbers in the network or discover those numbers. And there's a lot of benefits of doing this. So one of the benefits is that you will, in general, with a few exceptions, you'll get an exponential reduction in the memory, storage, and computation time needed. But best of all, you'll get insight and interpretation. So in physics, we've gotten a huge amount of this, partly because our problems are so structured to begin with. That's something I'll come back to a little bit. It's like as if we had sort of synthetic data in a sense, but we know a lot about our problems at the outset. but also because these tools have enabled us to ask questions that you just can't ask of other tools, these tensor network tools. And then, you can do very interesting things like estimating missing entries, developing more and more great algorithms and things. And then in terms of notation, I'll be using throughout this well-known Penrose tensor diagram notation, which I think you all know, but the idea is that you have a tensor and you write it as a shape with lines that are the indices. And here's just some low order examples. And the good thing about it is that you don't have to write the names of indices so much. So you're freed from having to have indices with subscripts with their own subscripts and this sort of thing. And then the main rule is that joining lines implies a contraction. So this little guide to the I line becomes the whole notation, and then you can just start dropping the indices altogether. It's easy to see when, for example, results are scalars versus vector value results. And just to emphasize that this is an entirely rigorous notation, that you can express almost everything in this notation. So it can just be very powerful for insight and for efficiency of notating things. So, as we all know, one of the most discussed and best understood examples of a tensor network is the tensor train or matrix product state, which has been, studied quite in depth. And there's a lot of algorithms, like we just heard about parallel algorithms for them even. And the main, control parameter of this is just kind of to set up a typical way of looking at tensor networks. The main control parameter is the bond dimension or tensor train rank. And if you can get away with this being a modest value, you can get massive compressions. But most interesting to me is that you can carry out a lot of important algorithms directly in the compressed form without really leaving this compressed space. So you can, as we saw, you can sum to MPS, staying always in this kind of MPS manifold. In fact, you don't even have to form this direct product form. You can even kind of just imagine it, and that leads to algorithms where you take advantage of the sparsity, and you can do things like the parallel algorithms we just saw. But you can do other things too, as many of you know. You can also even multiply, say, an MPS by an MPO, which would be a matrix-like MPS network, and do that all in the compressed form. And if this MPS represents a probability distribution, either directly or through this squaring approach that physicists use because of quantum mechanics, you can carry out perfect sampling of the you can perfectly sample, without any autocorrelation effects from that distribution afterward. And in quantum physics, where this tools have been used for a while, and again, the problems are very, very structured and well understood to begin with, has emerged a very rich theory and deep understanding of like how to kind of pair these tensor network architectures with certain, what you could think of roughly as like data classes, but it's really more like sets of distributions. And so really we would think of them as wave functions in physics, but wave function is just jargon for joint probability distribution of n variables written in a funny way, where you square to get the probability. So it's really like bunches of probability distributions of different kinds with local correlations between the variables and some spatial localities and spatial setting. That's really what all wave functions are. They're joint probability distributions. And in this setting, there was already a very good understanding of what data goes with what tensor network architecture, like which one naturally can capture those correlations fully. And the understanding, for example, is if you have a 1D system where the spectrum of the Hamiltonian has a spectral gap between the dominant eigenvector, not accounting for degeneracies, and then the subleading eigenvectors, then there's a proof by Hastings that all such systems can be captured, all such distributions can be captured by a matrix product state. So this is rigorously proved. And then there's a very good understanding that there's kind of there can be logarithmic corrections to that situation when the gap collapses, which we call a critical system. And then there's this Mira architecture, which is known to capture that setting. And then in 2D, there's an emerging understanding of how to capture gapped systems and even certain gapless systems there and so on. So there's already this rich pairing between kind of data and architectures that's happened there. But more broadly, we could imagine, we already are seeing, right, this conference is evidence of that these tools, thinking of them, as having to do with physics was a bit narrow. And that really they could be viewed very, very broadly as just a general power tool for doing linear algebra in exponentially high dimensional spaces. And even concepts that seemed to physicists or would seem like highly physics specific concepts could have a lot of value outside of these settings. So one example is that physicists will talk about entanglement entropy as a main way to think about the like whether a tensor network approximation is going to succeed for some distribution, or what we would say some wave function. And looking at it again, you could really see that what it is it's just a different measure of multilinear tensor rank. So it's like instead of looking at the tensor train rank as a integer and saying, what is the rank? It's more like taking the singular values when you do the TT-SVD algorithm and squaring them, looking at those values and then saying, what's the entropy of that distribution? And it's a bound on rank, but it's a more informative number because it tells you also about the distribution and not just how many are non-zero. So just these ideas actually do come over surprisingly, even though they seem at first very, very physics specific. So I'll comment on another measure like that later. So now switching gears a bit, that was just more introductory, just to sort of give some updates about what are some activities maybe a bit better known to physicists, though some of them are in the machine learning community, where the idea of using tensor networks as function approximators in machine learning is having some interesting developments and new architectures are being explored. So stepping back for a second, the setting here is generally always this idea that was put forward by a few groups in 2016 of that we could get a big tensor to appear in our machine learning model by first mapping our data, it's a nonlinear feature map to product features, meaning like a tensor product feature map. So you take each component of this input vector X, which might, is an n-dimensional, not a very too high dimensional thing. And then each component parameterizes a small vector, like a dimension 2 or dimension 3 vector. And then we formally take a tensor product of all those vectors that come out. And now we're formally in an exponentially higher dimensional space. So we can, now a linear classifier suffices to basically do anything. So then we can enact that linear classifier by compressing those linear weights with the tensor network, that idea I mentioned earlier. Here I'm just showing a matrix product state tensor network to be concrete. And this will evaluate our model when we contract all these tensors together. Here's just showing a model that outputs a scalar, but you could have vector valued output and other things. Then you can just pick some kind of cost function for some kind of regression, supervised learning, unsupervised learning. Then say use gradient descent in an alternating least squares or one site DMRG manner, and you just can write the gradient of say this tensor is actually this network with the tensor removed. That's easy to show by linearity. Then you just have to do these tensor contractions and get the gradient, use it to update this tensor in more or less sophisticated ways. And now you're doing machine learning using matrix product state weights. So that's kind of the basic example in the MPS case. But now this idea has been successfully ported to other kinds of tensor networks, some that are very closely related and some that are much more sophisticated. So I'll just go through these examples. So one example very briefly is the idea of using infinite matrix product states. So these are translation invariant matrix product states which don't terminate, and where every tensor, say, is the exact same. So right away, you have a model with very, very few parameters, and you can do things like optimizing them in parallel in ways analogous to what we just saw in the previous talk. And then this group, based in Mila in Montreal, but also with John Turilla, who's at City University here in New York, applied this to learn synthetic data that are these kind of model languages with model grammars. And these are, even though they're synthetic, they're actually very, very challenging to learn, and found that in many cases they could get either equivalent or superior results to LSTM recurrent neural networks. And best of all, they could see that they could train on shorter sequences up to a certain size, then deploy the model on even longer and longer sequences and see correct results. And so it's really learning. It's really learning the rules of the grammar and not just interpolating in a small set of examples and a set to a certain length output. Another architecture that I'm particularly interested in, trying more in the future. I don't think I have a slide about this, but there's a really nice work arguing that this architecture is especially powerful over matrix product states. Is this architecture called a locally purified state, and it's an idea of saying that you have a network that looks kind of like an MPO, where you would have two external indices coming out of every tensor, and otherwise they're contracted in a chain like MPS or Tensor Train. But then you don't have to have the second kind of index on every tensor. You could just have it every so often, or you could have it on every tensor. It's a little bit flexible there. Then your probability distribution is formed by squaring these two rows together, then taking the diagonal of the resulting tensor network, meaning that the variables on the top here and on the bottom here have to be taken to the same value when you evaluate like a probability of a certain input. And then this is proven to have much more expressive power. This is work by Ivan Glasser and Jens Eisert. It's proven to have much more expressive power than a matrix product state, and yet it's still very efficient to optimize and easy to work with. And a group at Google X just last year used this to do anomaly detection tasks and found that for kind of heterogeneous tabular data sets, these are some pretty standard like UCI data sets, I think, that they could get state equal or do better than state of the art. This is their results in a lot of cases over certain like neural network based approaches. And another work that is much more inside of physics, but this is where I think it's a really neat area for applications. We don't do a whole lot of machine learning in physics until recently. So then tensor networks are a pretty natural fit for us, is doing this thing called quantum process tomography, which was done in this work, I think, for the first time in a scalable way. And so this is work by Giacomo Torlai, who's now at Amazon Quantum. The idea here is that you treat a quantum circuit, basically a quantum computer, as a black box, and you feed in input bit strings and you get output bit strings. And this circuit could be noisy, it could have errors, and you can actually learn what's called the Choi map. It's just basically like a black box machine that implements that whole circuit. So you can actually learn that from these input-output pairs, and it worked really well. Let me see how my time is going. Then, a couple more examples. One briefly is that it's now been, machine learning of tensor networks has now been done successfully for 2D tensor networks, for projected entangled pair states, as they're called in the physics jargon. But basically, it's just the 2D version of like a tensor train or MPS, though it has loops, so it's much more challenging to work with. But using this kind of same framework for learning that I mentioned with this tensor product feature map, and they got comparable results to state of the art on both MNIST and fashion MNIST image data. They see promising things like they can go well beyond what you can get for matrix product states, including starting to seeing overfitting a little bit. And they tried some interesting twists, like using convolutional neural net layers. But the big drawback, that helped a lot. The big drawback, though, is that it was very expensive to do this. So they basically burned a lot of GPU time and had to work really hard to pull this off. So it's a bit still more in the like proof of principle range. And then lastly, a work that I was involved in recently, just kind of an exploratory work to see, there's this mirror architecture, which has a lot of expressive power, but it has some algorithmic drawbacks too, but has very interesting, theoretical connections to things like wavelets, actually. How could it be used in machine learning in some interesting way? So I did this work with Justin Reyes, who's at University of Central Florida, where we just came up with an architecture where we used fixed mirror layers, meaning we just made these by hand. And they're fixed parameters. We're not training these parameters. All the trainable parameters are at the top in a matrix product state that kind of rides on top. So it's this idea called like a mirror curtain architecture. And then we can train and get good results on, we tried audio data, just trying to do like binary classification of audio data, and got nice results. Then what we were arguing is that a nice capability of doing things this way is that we could understand what these layers are doing, because they're equivalent to a certain class of wavelet that we just hand designed by parameterizing in a certain way. But then we could fine grain the model afterwards. So we could say, well, did we get the result we wanted? No, but it was pretty good. So we could then controllably fine grain the MPS back down a layer by absorbing all these in a controlled manner into the MPS and get one with twice as many indices, and then keep training. And we're rigorously guaranteed to start out at the exact same performance level that we had, and then just improve more. And now our model can sort of see the data more in a more fine-grained way. And there's a lot of potential follow-ups of that work. That was just more of a proof of principle starting point. Okay, so then in my remaining time, let me just talk a little bit about an area I think is like the most exciting to me, and it involves a lot of work by others, but some things that I'm pushing on, which is really theory and algorithms. It's like understanding some things about exploiting the fact that we're working with tensor networks to try to really understand some things deeply, and pushing what we can do beyond, say, using like gradient descent. So first of all, in terms of understanding, this is all work of others, but it's what I'm excited about. It's the question of why should we expect tensor networks to work for machine learning at all? From a physics point of view, you would look at images, say if we're thinking about image data, which is what these works considered, you would say these look way more complicated than some little spin model thing that we might study or something. So why should this work? Why on earth should these be low entanglement? Or you might look at like text data and say the same. You should say, at a minimum, these are going to have power law correlations, and maybe it's even worse. And why should this work? Because in physics, we have this understanding that low entanglement, which is really just a notion of rank, only happens in kind of very special situations where there's a lot of locality. So you would think, no, that there's no real reason why this should work. And there was some evidence starting to appear that indeed this program of doing machine learning, especially of 2D images, was sort of doomed with tensor networks. In particular, there was this paper just from last year by a group at Google X, this Martin et al. Paper, where they said, let's make a tensor network by summing images. So let's sum images that are mapped in the way I mentioned to these product features, and use the fact that we can think of them as matrix product states and some matrix product states, and just keep summing them more and more and more. And they used a kind of clever algorithm to work around some of the costs and to then exactly obtain the entanglement entropy that would result. And they found it just grows and grows and grows, sort of out of control as you sum more images. It grows in a way that you could call like a volume law, like kind of a worst case that you could imagine. So they were saying, maybe this worked for MNIST and a couple other examples, but it's not going to really work for, say, generative modeling of most image data. That would be the one conclusion you might think from what they showed. But then two very recent papers, literally just from a few weeks ago, are offering kind of a more, they're sort of on the other side. They're offering a different perspective. First of all, they're looking at a different quantity. They're looking more at like mutual information of a classical probability distribution. So saying, what information is kind of shared between two partitions of the data when we look at it as coming from a classical distribution. They talk a good bit about various strategies to estimate the mutual information of image data. They pursue some different ones. Here's one paper and the other. And they do some really nice things. So one of the papers by Convey and Huggins et al. First does a warm-up study of synthetic Gaussian data with different correlations. And then they found that when they studied the mutual information of the synthetic 2D Gaussians, that realistic images have similar mutual information scaling properties to that of a nearest neighbor correlated Gaussian. So it does imply that there's a lot of locality in images. They look at MNIST and the tiny image data set. This other paper by the group of Ignacio Serac studied both text and images, and they found some similar results on images, although more suggestions that the correlations may be more challenging than this paper suggests in images. And they studied text, and there they found, tentatively, I would say that text looks to be beyond the typical scaling that things like matrix product states capture. It seems to be more in this volume law regime. So at a minimum, you might need these things I mentioned, these locally purified states, but the situation may even be worse for text. So I think some more thinking is needed about that, but I think that's the sort of tentative takeaway. But on the more positive side, back to this much more pessimistic result by this Martin et al. Paper, the Convey paper made a really good point about it. They pointed out that although this calculation is certainly a correct calculation, it may just be an overly pessimistic one, something like a loose upper bound, but that's too loose, roughly speaking. Basically, it's like they're studying the feature map itself. They're not, say, bringing into the idea that when you then compress and throw things away, you could still obtain good results, good enough for some machine learning objective, even though it's not equal to this actual sum of all images that they defined here through that very, very sort of sensitive feature map that is proposed. There's other things too that could mitigate this result. This is still a tiny fraction of all conceivable images. And if you were adding things like blurring and distortions, this could actually help a lot with the scaling to kind of simulate having much more images than you actually have. And then this is really all about generative modeling. Supervised learning may be in much better shape. But it's interesting that these questions can even be posed and answered, and tensor networks kind of inspire this sort of thinking, I would say. And then now just in the remaining few minutes, let me talk a bit about algorithms. And there's just a lot of great work going on in the math community and physics community too about developing more and more powerful algorithms for tensor networks like we just saw. So I just want to say, first of all, there's so many already. So there's, I think, a lot of work to be done taking advantage of the power of each of these or certain things they offer. For example, some of these algorithms are deterministic. So there's a lot of theory that I think can then be built on top of these deterministic algorithms that can go, much beyond, say, the situation with neural networks, where a lot of work has to focus on like dynamics of gradient descent. Here, some of these algorithms being deterministic, they don't really have dynamics. It's much more of like one can really kind of just follow through them step by step and really understand what each step is contributing to the final result and what that says about things like, say, generalization or how much data is needed to obtain certain results, or whether certain data is really compatible with certain architectures. And I'll mention, in particular this algorithm and kind of touch on this one as well. So one setting, just mentioning a couple of papers, one I was involved in, where algorithms were sort of paired with data in a machine learning setting, and I think some nice insights happened, was the setting of thinking about how would a matrix product state learn this very challenging data set called the even parity bit string data set. And this data set is defined as just all strings of length n, some length n, which might be 10 or 20, where you always have an even number of ones. So it's exactly half of all the bit strings. If you see an odd number of ones, it's not in the data set. So then to model this, we use the same kind of feature map where we say, okay, a 0 bit gets mapped to the first standard basis vector and a 1 bit to the second standard basis vector. And then we formally take a tensor product of these, and that's our feature map. And then we try to learn to generate back this data with a matrix product state. So we want to learn the MPS where we could sample from and get all this, get this entire data set back. I should mention that one neat thing about the setting here is that even though there's a very challenging distribution, for example, all the local moments, or all the low order moments in this data are trivial. The only real information is in the global. You have to look at every bit to know whether the total is even or odd. That being said, this can be exactly generated by a rank 2 or bond dimension 2 MPS exactly. It's easy just to write it down. So we know we're in the right model class, but it's still very hard to learn nevertheless. So there was a paper first in 2019 by James Stokes and John Turilla, two people that I know here in New York, where they were studying this task, and they were asking about, could we pull this off, and then could we develop a really nice algorithm to do so in this generative modeling setting. And they realized that in this setting, you can actually not only do kind of alternating least squares DMRG with gradient descent, you could actually write down the exact solution for the how to update that each tensor as you do them one at a time. So they wrote down an exact solution for that's sufficient, and they could do this. Then they could use this exact solution, which is nice, to keep locally improving the MPS, and they get great results. They were able to generate back the distribution up to, I think, length 16 bit strings, which was very impressive, actually. So that was nice, and you could use kind of geometric high dimensional reasoning to develop this exact local update. You could push this pretty far. It scales linearly in everything, data length, the training set size. The big drawback is it needs a good initial state. So it can get stuck. It can fall into a local minimum, even though you're doing this optimal update. So that was the drawback. So then that led us to think about a different algorithm. I won't, unfortunately, have a lot of time to discuss this one, but it's deterministic. It's very interesting. It's basically the idea that SVD can be carried out by squaring a matrix and then diagonalizing the resulting Hermitian matrix that you get that way, which in physics we call a density matrix. Then that gives you a unitary, and that unitary, it turns out, just is the first MPS tensor that you need. Then you can iterate this and get the second, the third, the fourth. So you can basically just crank through deterministically and just sort of print the MPS one tensor at a time, and then you're done. And there's no kind of additional sweeping or gradient steps or anything. At the cost, though, of it can scale a little bit worse than other ones, but it's still polynomial. So we did the learning by defining a kind of idealized target tensor, which is all the training data that we have. You can run that data through this deterministic density matrix algorithm. Each time you get a small matrix, you diagonalize it, it gives you the first MPS tensor. You take those, apply them back onto the data, and just iterate. And the nice thing is, because it's deterministic, we could study the whole thing in this setting of this synthetic data. The big drawback is it scales quadratically, though, in the training set size, but in every other way, it's a very nice algorithm. But by following through the steps, we really wanted to do it because we could follow every step. We could use, we could study the statistics of a typical training set that you would draw at random from the full data set. Then we could develop statistical averaging to understand what numbers would on average be in these small matrices that we diagonalize to get the MPS tensors of Tensor Train course. And then we could develop a predictive theory of generalization that would say, if we are given this fraction of all the data, then typically we'll do this well at generalization. And the theory and the actual experiments when we run the algorithm don't agree too well in this tiny limit here, but then very quickly they catch up. And I don't know if I have a zoom, no. But when you zoom in, the agreement is really good. And we even, to the degree that it differs, we even understand that. So we were able to really develop a theory of generalization in this controlled setting. So I think it could be, this work could then be generalized a lot to like other synthetic data and improved in terms of our estimates and everything. So I'll wrap up by just saying that there's still a lot of downsides to doing machine learning this way. I think the costs can be very high. Scaling can be worse in certain cases, like here it's quadratic in training set size, so it doesn't always have to be. And there's still a lot to figure out about what kind of data is this really going to work for, and what are the best choices to make. But then I think there's huge opportunities to improve on all these things. For example, there could be more use of sparsity or symmetries, like block sparsity. We heard that idea mentioned on Monday, I think, within the models. Use the power of infinite tensor networks more. Use symmetries a lot more. And I think we can feed the theory, especially back into the algorithms to learn with less data, and some of the ideas for how would be studies like this, where we actually make predictive models of generalization and understand what the algorithm's doing. And then I just think we could push a lot on the frontiers of things like interpretability, understanding, generalization. We could really understand more and more of what data is learnable, and it's already happening in those works I showed. What data is learnable by certain architectures? I mentioned a few times this theory of generalization. There's a lot of things we could improve on that. And I think it's going to all feed back into making these models more practically useful too. So thanks a lot.